The second module of this appendix is on Jensen's inequality, which is the subject of Appendix C. We've seen Jensen's inequality, or will see Jensen's inequality, depending on the order in which you do these modules. It comes up in many places in finance as in other areas of mathematics. It's a very useful result. And in order to state it, we first of all need to review the notions of convex function. So we'll say that a function is convex on an interval if on any subinterval the value of the function at any point in that subinterval is below the interpolated value of the function. And so graphically, we can just look at a quick graph of what that means. Here's an example of a convex function. It says this interval, let's say I let f of x be 1 over x. F of x of 1 over x is convex because if I take any interval CD and I now connect, convex says that at any point, let's call it A, that if A is equal to a combination, a linear combination of D and C, let's say it's equal to lambda of D plus 1 minus lambda of C. So, for example, if lambda was a half, it'd be the midpoint. If lambda was a fourth, it would be a fourth of the way between C and D and so forth. So it's just an interpolated point. It says that if I look at f of A is going to be less than or equal to this same combination of the function values, which would be this point. Lambda f of D plus 1 minus lambda f of C. That's all it means. It means that at every point A in that interval, the function value is below the interpolated endpoint function values, which graphically simply means that the function is below, this is sometimes called a secant. A secant is just a straight line segment that joins 2 points of a curve. If we take any secant, the function value on the interval is below or at least not above, less than or equal to. It's less than or equal to the value interpolated. This is the opposite of concave. Concave means the opposite. A function like this would be concave. It means that if you choose any secant value, the function values are above their interpolated endpoint values. So we'll just state there's a Jensen's inequality for both convex and concave, and you simply change the inequality and you get the other. So convex says that the value of the function at an intermediate point is no bigger than the interpolated endpoint values. An easy way to check for convexity, if it's a function whose graph you're unfamiliar with, usually if you know the graph or you see the graph, it's visually apparent if it's convex or not. But for functions that have two derivatives, knowing that the second derivative is positive is enough to know it's convex. Indeed, if I say that the second derivative is non-negative, that implies that the first derivative is increasing, or at least non-decreasing. Non-decreasing. And if we go to the example, we can see that in this convex case, 1 over x is convex. If I look at its second derivative, first derivative is minus 1 over x squared, and second derivative is 2 over x cubed. It's a positive quantity. So this is convex when x is positive, and we can see that here, and that in fact the derivative, the first derivative, which is the slope, is increasing. It's an increasing function. If you graphed the derivative function, it's an increasing function. So that's a convenient way of checking. And of course, 1 over x is actually concave when x is negative. And we can see that because it has a negative second derivative. In the same way that a positive second derivative implies convexity, a negative second derivative implies concavity. Just the sign switches. And again, we can see that here. So examples that we will commonly use in the finance of this text are e to the x or e to the minus x, both of which are convex. And we've had a number of results in various modules where we state, we draw a conclusion about some important matter by using Jensen's inequality. I'll review a couple of examples.